We're starting chapter 5. This is 5.1. We're talking about direct variation. The distance that a person can jog is related to time. If you're jogging at a constant speed of 100 meters per minute, how far can you jog in 10 minutes in 1 hour? So that's what we're going to investigate. It says, what is the relationship between distance and time? Susan can jog at a steady pace of 150 meters per minute for the first hour. Create a table showing the distance that Susan jogs in 0, 1, 2, and so on up to 10. All right, so the first thing before, it actually asks us create a table. So we don't need to know dependent versus independent yet. We'll just create the table. So distance and time. So time is 0, 1, 2, 3, 4, 5, 6. And it says 150 per minute. So in 0, she does 0, then she does 150. Okay, so we create this table. We know this because she says she can run a steady pace of 150 per meter. So every minute, I just added 150. Okay, and distance is in meters and time is in minutes. Any questions about how I created this table? Pretty simple, right? Next, it says identify the independent variable and the dependent variable, and then graph this relationship. Dependent and independent. I was shocked on the test that somebody actually got the independent-dependent one wrong. A couple people. Max?
The independent variable is time and the dependent is distance.
Good. Again, one of the key indicators, so we talked about measured versus chosen. Sometimes we can have some kind of exceptions to that rule. But another one we talked about is kind of the gap between the points. Okay, and we talked about the independent variable always having a consistent gap. Okay, so in other words, see this 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So there's a consistent gap of 1. In this case, the distance is also a consistent gap of 150, but that's not always the case. It's not actually usually the case. Okay, unless it's a perfect variation, we don't always have this gap being the same. Okay, but when we have the independent variable, this, because it's the chosen variable, it usually has always the same gap. Okay, so that's another big indicator. So the spacing between the x values. All right, so we want to graph this. We're going to put the independent time down here. Okay, so we create our graph. Again, it's not perfectly accurate, but you get the idea. Okay. It says, describe the shape of the graph. Where does it intersect the vertical axis? Okay. Anybody? Christian?
0 minute.
Yeah, so it intersects the vertical axis at 0 minutes or 0 meters. And what's the shape? AJ?
Positive linear.
Positive linear relationship. Very good. Very important that we say it's linear. Okay? Because we've learned that, right? It's part of the vocabulary. Describe the shape of the graph. What is it? Write an equation to find the distance d in meters that Susan jogs in t minutes. An equation to find the distance. Tyler.
150 T.
So d, right?
So depending on how much time she had and what distance.
Yeah, very good. That's a good equation. Does everyone recognize why this should be the equation to calculate the distance? Sal?
Because every 1 minute, you're going 150 meters, so
Right, so if we substitute t in each time here, we're going to get this value of d, right? Sub in 6 for t here, I'm going to get 900 for d. Very important, guys. This is the first time you've seen this, that you understand how this equation relates to this table and to this line graph. Okay, so if you have any questions, please ask me now. All right, use the equation to determine the distance that Susan can jog in 40 minutes. All right, so our time goes all the way down to 40 minutes. So before we used or came up with Tyler's equation, we would have had to do what to find out how far she jogs in 40 minutes? Yeah. Right, extrapolate. So we would have had to take this graph and gone all the way over here to 40. Okay, which would have been, somewhere way over here. It would have taken quite a bit of work to figure that out. But now, because of this nifty equation, how can we figure it out? What can we do, Alvin?
150 multiplied by 40.
Sorry, say that again?
150 multiplied by 40.
Right, we're going to take this value for t, we're going to sub it in for t and figure out our distance. So 150 times 40, we get 66,000 meters. Any questions? Yeah.
So you know how you said that the distance was not always going to be like equal every single time that
Yeah.
this is? How would
Yeah.
it be making an equation for next time? Because like let's say the distance isn't always equal after every minute.
Yeah, you'll see that, okay? We'll get to there when it comes up. It's going to come up in the next couple examples. Any other questions? All right, so we know that she can run 6,000 meters in 40 minutes. AJ, is that fast? How fast is that? What's 6,000 meters in running terms? You wouldn't say I ran a 6,000 meter today. What would you say?
6K.
Right, 6K in 40 meters is fast?
It's okay.
It's okay, yeah. It's not very fast, though. It's like a jog, right? Like a light jog. Yeah. The fact that she's moving for 40 minutes, though, is not bad. F, consider the distance Susan's jogged in 2 minutes. What happens to the distance when the time is doubled? What happens to the distance when the time is tripled? Yeah, Adam.
If the time doubles, the distance doubles.
Right. So there's what we call a direct variation. Okay, because if time doubles, distance doubles. All right, so there's a direct relationship between the time and the distance. Okay. All right, Trish's steady jogging pace is 175 meters per minute. Okay, so this is Trish now, not Susan. Repeat step 1 using Trish's speed. All right. So we're not going to go through it all again, but what do you think Trish's graph is going to look like? If this is Susan's, Susan runs, remember, 150 meters per minute. If I was graphing Trish now, what's it going to look like? Luca at the back. What do you think? Not sure? Here, I'll help you out.
Yeah, sorry, I can't find her data.
Sorry?
I can't find her data.
It's 175.
Yeah, we haven't made it yet. It's here, Trish. It's 175 meters per minute. So what do you think her line will look like? Or her?
It's gonna look more steeper.
Yes, good. So like this?
No, it's gonna look.
Right. It's gonna look like that, right? This is gonna be more Trish. Okay, and why do you say that?
Because it's increasing at a faster rate.
Right, so she's traveling more further in less time. Okay? Very good. So this is Trish. And what do you think Trish's distance formula is going to be? Luca, right here.
D equals 175 P.
Excellent. All right. Any questions about that? Okay, let's reflect. Describe how to develop an equation for distance when you know the average speed. Yeah.
Well, you can use Dummy's triangle to rearrange it.
Right, so we know the equation distance is equal to speed times time. Right, so that's how we would do it. All right, who would like to read? Matthew in the front.
The relationship between distance and time is an example of a direct variation. For example, the table shows distances traveled in various time periods at a constant speed of 10 meters a second. When time is multiplied by a specific number, distance is also multiplied by the same number. Another way to describe this direct variation is to say that the distance varies directly with time. In a direct variation, the ratio of corresponding values of the variables does not change. So if d is distance and t is time, then d over t equals k, where k is called the constant of variation. Multiplying both sides of the equation by t gives d equals kt. For the data in the table, d over t equals 10 or d equals 10t, the constant of variation is 10.
Good, so again, they're just using that Dummy's triangle and showing you the different variations. Direct variation, a relationship between two variables in which one variable is a constant multiple of the other. So again, direct variation looks like an equation that looks like this. Okay? Constant of variation. In a direct variation, the ratio of corresponding values of the variables, often represented by k, or the constant multiple by which one variable is multiplied. If d varies directly as t, then the constant variation k is given by d over t. Okay, so in other words, that number that it varies by, that's your k value. Okay? You can either solve for it directly like this, or just know that k is the constant variation term in front of the second variable. Example 1. The Frederick family travels 250 kilometers to a relative's home. The distance d in kilometers varies directly with time, t in hours. Find the equation relating d and t. If d equals 43, when t equals 0.5, what does the constant of variation represent? All right, so we're trying to develop an equation here. We're given d and t. We're told that they vary directly. Okay, so what we really want to solve for is what variable. If we know that the constant relationship is determined by d equals kt, what variable do we want to solve for here to get a generic equation for this particular example? Hugo.
K.
Yes, good, k. So we want to solve for k. We have d, we have t. How can we solve for k? Sebastian.
Well, you would define the distance by the time.
Good. K is equal to d over t. So d is 43 and t is 0.5. So we're going to get 86. K is equal to 86. Well, if k is equal to 86, how can I rewrite my direct variation equation? Robert. It's okay, that's why we're learning it. D is equal to KT, Robert. What is K?
86.
Good, 86. So what would be our equation for D?
D equals 86K
Nope.
times K.
No, 86 is K.
Oh, sorry, T.
Good. D is equal to 86T. Okay? So this is a scenario where they gave you distance and time and they told you that it's a direct variation. Okay, so if that's the case, then you got to solve for K. That direct variation constant, and then from there you can get the equation. Yeah, AJ.
What does K stand for?
They use it for constant. I know you would think it would be C, but they use K as a constant. I don't know. Doesn't really stand for anything. Yeah.
So where does the 250 kilometers come?
Uh,
Ask that too.
okay, we're gonna find out. I think it's probably in B. Travels 250 kilometers to a relative's house. All right. Use the equation to determine how long it will take. Yeah, so it comes up in B. Okay, so that's A. We develop our equation. What does the constant of variation represent? So what does 86 represent? In our dummies triangle, D equals S times T, right? So in this case, 86 represents what? Matthew, in front of Max.
The 86 shows the speed they're going.
Yeah, speed, good. Yeah, it's kilometers per hour. Very good. So in this case, the constant of variation represents speed. Okay, B, use the equation to determine how long it will take the Fredericks to reach their destination. So here's where the 250 comes in. Who was asking that? All right, Adam, so how long will it take?
86 kilometers an hour. 250 divided by 86.
B, right. You're going to take that 250, you're going to sub it in for distance. And now we want to know how long, so we're going to solve for T. 250 divided by 86 is 2.9 approximately. And T is in hours. Any questions? So if they ask you for how long, you're solving for time. Use the same formula. Now you just rearrange it and solve for T. Sub in for the known values. In this case, it was 250 for D. Rearrange, solve for T. Any questions there? All right. Example 2. Steven.
Amir works part-time at a local bookstore. He earns $7.50 per hour. Describe the relationship between his pay in dollars and the time and hours he works.
All right, so let's do that. Nicholas, describe the relationship between his pay and the time.
So, would be, his pay is equal to 7.5 T.
Good. Yeah, so his pay is equal to 7.5 T. So in trying to describe it, Nicholas made the equation already. He said, well, I know his pay is going to be equal to 7.5 times T, where T is what?
T,
T is what?
T is P over 7.
No, but yeah, but T in general was what? T is the most obvious thing. Time, right? Yeah. I'm just looking, I was looking more, not so much for time, I was looking for the units, okay? Hours, right? T is his time in hours, okay? That's important because in this question, guys, one of the areas where they'll mess you up is they'll say, oh, he worked for 65 minutes, but you've developed your formula in hours. So you have to take that 65 and divide by 60 to get the time in hours. Does that make sense? Because there's 1 hour, 60 minutes in 1 hour. So you divide whatever time in minutes by the hour. Okay, so that's A. B, illustrate the relationship graphically and represent it with an equation. Okay, so we've done the equation part just in trying to describe it. Let's zoom in here on our graph. Okay, so here's our time worked, and here's our pay. Okay, and we know this because, again, he's getting $7.50 per hour, which is given in the question, $7.50 per hour. So these values here, time worked, these were chosen. Okay, I've chosen these values just to give me a graph. So those weren't given anywhere, they were chosen, 0, 2, 4, 6, 8. And notice how they're constant. The gaps are constant. These are constant again, but next lesson they're not going to be constant. Okay, it's just the reason why they are is because we're dealing specifically with direct variation. All right, so then we calculate our pay here and we make a graph here. Any questions about how we graphed it or made the table? No? All right. C, 1 week, and finally write the equation. K is 750. Here's our equation, which we got earlier. There it is again. Finally, C, 1 week, Amir works 9 hours. Find his pay for that week. So again, before today, you might have had to interpolate here. You might have had to go to 9 like this, and then go across and say, oh, it was about $65 that week, right? But now we're going to use our equation and figure out the pay directly.